In the last lecture, we studied about what is moment of force, and we came to know that for a body to rotate, to produce a turning effect, we need to have a pivot, and there is a force, and there's a distance, a perpendicular distance. The product of the magnitude of the force and the perpendicular distance, this causes the turning effect, and that we call moment of force. Now we are trying to understand here a couple of forces. So if you look at these few examples, we'll try to figure it out. What is this couple that we are talking about? So when we talked about turning force, turning effect, when we talked about this turning effect produced by the force, basically what exactly happens when you apply a force on a body which is pivoted, it produces, we see the effect is rotational. The effect is turning effect. But quantitatively, if you apply the Newton's law and try to understand exactly what are the forces acting on it. So when you apply a force, and since it is pivoted at a point, there is a reaction in the opposite direction. And this basically is responsible for the rotational motion. Now this reaction force, the pivot is happening right at the pivot. So the moment, because of this force, the moment of the force is zero. Why? The distance is zero. So we just see one of the force which is applied, and there's a rotational motion. However, to understand this couple, we take this example of turning a water tap. So if you carefully look at, the pivot is somewhere in the middle, and we turn it round like this. So we, with our fingers, we try to provide force, apply force on either way, on the either side of this tap handle. One force is in this direction and another force is in this direction. The magnitude of the force is same, but the directions are opposite to each other. But we need to ensure that these two forces that we are applying does not act along the same line. It acts on a different line. The line of forces are different, but they are equal in magnitude and opposite in direction. And this eventually you would find that you are able to rotate the tap, turning a water tap. Similarly, when you try to open the bottle, right? So if you see the cap here, you apply the force in this direction. The other finger applies the force in the opposite direction, not in the same line. So there is always a distance between the point of application of both the forces and the resulting effect that it's going to turn, and you are able to open the bottle or close the bottle. So it's the rotational motion which is happening. It's because of two forces that we are calling pair of forces, and this pair of forces forms a couple. Well, if you look at this lock and key mechanism, you would find that the same thing is happening, right? You insert the key in the lock, and when you turn it round, so the pivot is somewhere here in this axis, lies on the axis, and you're applying the force on the opposite direction. Two forces of equal magnitude, but there's a distance between the application of the point of application of these two forces, and then we find that you get the lock opened up. Similarly, if you carefully look at this steering wheel, right, turning a steering wheel. So here you apply a force in this direction, here you apply the force in this direction. So these two forces form a pair of forces, a couple of forces, and there is always a distance between. So the point of application of force is in this direction, and here is in this direction. They don't act on the same line, and there is a distance that separates these two forces, and the resultant effect is that it rotates, right? So they are separated with this perpendicular distance, and they don't act on the same line. So for rotational motion, it is very important to understand that there is a couple that is acting, that is the couple of forces, a pair of forces. Now let's understand quantitatively. Suppose we have one rod here, and this rod is pivoted. The fulcrum of the rod is somewhere here, suppose, and the distance from either end is, suppose this is D1, and the distance is d2. So the rod is of length d, and d is equal to d1 plus d2. So we apply a force here. Let me show the force here. This is a force applied in this direction, and another force is applied in this direction. And there's a center point here, and this is the pivot. So if you want to figure it out, what is the moment of force because of the resultant moment of force. So moment of force because of this, right? Because of this side, that is, if you consider this distance d2, moment of force in first situation would be force times d2, right? Moment of force in the second situation, so this is first situation, first force, if we consider the second moment of force, moment of force at the other end due to force at the other end this equals F times d1, right? So this is 2. Now this force in this side, if it is producing a defect, the moment of force here, this is anti-clockwise moment and this is clockwise moment. So if you add it up, therefore the resultant moment of force or the torque, the resultant torque or the moment of force is equal to F times d1 plus F times d2, which means that it's F, if you take common, it is d1 plus d2, right? So F times d1 plus d2 is net torque, which means that the magnitude of force times the total distance, right? The perpendicular distance separating the two forces. So if you want to write it in words, the net torque or the net moment of force is equal to magnitude of either force times perpendicular distance between the two forces. So we get a formula here for the net torque, which is very important. It's the magnitude of the either of the force, which is F, and d1 plus d2. So d1 plus d2 is the separation between the two forces. So this is what we get to solve for if you want to find what is the net torque. Please take note of this. You can take note of this, and then we'll now try to understand equilibrium condition. So we'll try to now understand what is the equilibrium condition means. And this equilibrium condition, when we'll discuss about two kinds of equilibrium, which is static and dynamic. But first, let's try to understand what do we mean by the term equilibrium. In the context of force, when we talk of the equilibrium, when multiple forces are acting on a body, right? So what would happen? It could do two things. Either it would initiate a linear motion. It's going to change the state of the body. If the body is at rest, it's going to change the state. Or if the body is in motion, it's going to change the linear motion state of the body. That is one thing that a force can do. Another thing that we have learned the force can do is to create it's to initiate a rotational motion. So a force can either change the state of the body, right? So this body at rest, it can change the state if it is at rest or in linear motion. So two things are important. It can change the state of the body if the body is at rest or if it is in the linear motion. If it is at rest, it could be now moving. If it is in linear motion, it could stop. That is what the force can do. The force can also do one thing, and that is it could change the state. And this time, it changes the state at rest of the body, at rest or rotational, or in a state of rotation, or it is in a state of rotational motion. So a force can either change the state of the body if the body is at rest or linear motion, or it could change the state of the rest or the state of the rotation. So which means that the force can do two things. Either it could form it could enable the linear motion, or it could enable the rotational motion. Both things a force could do. So if a body is in equilibrium, which means that this linear motion and the rotational motion, both the situation is not happening. So the state of the body is preserved, right? It is preserved. So that essentially means that although the forces are acting, the state is preserved, and this particular situation is what is known as equilibrium condition or equilibrium state. So both situations could happen, but none of those are happening, and it is able to preserve the state. We call the situation to be in equilibrium state. This is the basic concept of this word, which is equilibrium. Now let's understand one by one, what do we mean by static and dynamic equilibrium? So you can take note of this, and then we'll try to check the situation when the body is at rest in a static position. What are the forces acting on the body when it is not moving, although there are multiple forces acting? So suppose you have a body here, and the body is placed on some surface, right? And multiple forces are acting on the body. So a book is on the table, and the book is being pushed, and whatever it is pushed this way, the book always has a mass. So certainly there is something which is known as weight, and we denote this by m times g from Newton's law. We'll come to know the mass when multiplied by acceleration due to gravity is giving you the weight of the body, and this weight acts downwards. You also apply the force on the body, but this body is not moving. What is the reason? The reason is another force is acting somewhere. Maybe the frictional force is acting in this direction, and the body is not moving, which certainly what we want to understand, that this condition the sum of forces is not causing the linear motion. So we say that the body was at rest and is at rest now as well. So the body is in a state of static equilibrium. Static equilibrium. So the state which was before, upon the force acting, the state is not changing. That's a situation of a static equilibrium. Is it clear to you? Is it clear to you all that in the situation of a static equilibrium, a body is subjected to multiple forces, but when you add up all the forces, the net result is zero. And this is the reason why the body stays in static equilibrium. All right, so let's now understand then what is dynamic. What is dynamic equilibrium? The body is in state of motion. Is it possible? Yeah, it's possible. You have a fan, right? Fan, you set the current in a particular value. Suppose you use a regulator in a fan and you set the regulator at a fixed value. So there is a current feed to the fan which is constant, and this fan is rotating. So as the fan is rotating, the blades are rotating. It's in rotational equilibrium. But look at it carefully. When you look at it carefully, you would find that some of anti-clockwise, if the speed is remaining same, but what is happening, the velocity is changing. So whatever is the blade that is fixed there, it's not going anywhere. The blade which is tied up to the central part of the rotor, that is not going anywhere because the force is acting. Although it's in dynamic condition, the force is acting on that blade is one of the force which is known as centripetal. The other force is acting as centrifugal. So both are balancing each other. So we don't find anything to get out of this condition. So it is maintaining that dynamic equilibrium. Another example that you can think of. Suppose you think of an airplane, right? There's an airplane. Suppose there's an airplane. Try to make it. Okay. All right. Now this aeroplane is moving with constant velocity, right? It is moving with constant velocity horizontally. So how it's possible? It is possible because the mass here of an aeroplane, suppose if it is m, so the weight of the aeroplane is acting downwards, mass times g, m times g, and there is a pressure lift in this direction. So this is upward lift, right? Because of the pressure created, upward lift. So if this weight mg balances the upward lift, this is in constant motion, it continues to be in the state. So that state is preserved, and this is a situation of dynamic equilibrium. So this is a situation of dynamic equilibrium. Similarly, you would find raindrops falling at constant velocity. So what is the reason? How the velocity gets constant? Suppose that raindrop has mass m, it has a weight then, m times g, it is coming down, right? And the viscosity of the air, the frictional force that is caused, or the atmospheric pressure is causing, the viscosity is causing the upward, opposing the motion. So if both two forces are balancing each other, although it's in constant motion, although it's in motion, it remains constant. So with constant motion, that raindrop is falling down. This is also an example of dynamic equilibrium. So how do we formally define its situation? In both the situations, what are the two conditions? You can take note of the conditions. The first thing required for this equilibrium to be maintained there, is the resultant of all the forces acting on the body should be zero. So let me write this here. So the first condition for a body to maintain an equilibrium is the resultant of all the forces acting on a body should be equal to zero. So conditions required for a body in equilibrium. First condition is the resultant of all the forces acting on a body should be zero. So this is going to prevent the linear motion. What could be another? The another condition could be the algebraic sum of all the moment of forces. The algebraic sum moment of all the forces on the body should be zero. So if these two conditions are met, neither linear nor rotational motion is going to be there, the net linear or the net rotational, and the body would be in equilibrium condition. So you take down these 2 points, and from here we can have a formal definition of principle of moments. So we can now write a definition of principle of moments. So according to principle of moments, in equilibrium, anti-clockwise moment is equal to clockwise moments. So suppose multiple forces are acting, so you can write that net anti-clockwise moment should be equal to net clockwise moments, and we get a formal definition of what we call as principle of moments. So these are few concepts which are very important to understand the behavior that a body could be exhibiting while the body is acted upon by different forces. So continue watching the lectures. In the next lecture, we'll be working on numericals. So watch it. Don't forget, subscribe, like, and share the video. Thank you.